This project was chosen because of interest in how and why airfoils need to change shape for different operating velocities, in particular from subsonic to supersonic flows. In supersonic conditions, shock waves develop over an airfoil, and the shape of an airfoil and its developing shock waves have an effect on both lift and drag. To understand this problem, a CFD model was made for a NACA 0012 subsonic airfoil and a Diamond supersonic airfoil. By looking at supersonic simulations of both airfoils, results are compared to understand the difference in developing shock waves and drag effects. It is important to know that the simulations are verified with numerical results if possible, to ensure that the simulations are showing actual physics. Therefore, the Diamond airfoil was compared to theoretical values using oblique shock equations. The oblique shockwave problem is given by a supersonic flow upstream that is redirected along the turn angle theta, resulting in the shockwave angle beta. The resulting velocity behind the shockwave can be broken up into normal and tangential components. Using the continuity and momentum equations, we find that the tangential component of velocity is conserved. Therefore, we can use just the normal component of Mach number upstream as an input into the normal shock equations using the following relationship. A normal shock wave is given by a shock wave that is perpendicular to its upstream and downstream conditions. Again, using the normal component of the upstream Mach number as an input into the normal shock equations, we get the following relationships. Once we find the normal component of the Mach number downstream, we can use a geometric relationship to find the total Mach number downstream, as given here. These show that an oblique shock is a function of upstream Mach number, turn angle, and wave angle. These can be organized into what is called the theta-beta-m relationship, in which we need two of these properties to solve for the third. Typically, we know an upstream Mach number, and we know the physical turn angle of our system. So we solve for our beta, or wave angle, and therefore we can solve for our downstream Mach number. The CFD simulation has an upstream Mach number of 2, and a Diamond airfoil that has a 10-degree turn angle on both the top and the bottom of the airfoil. The airfoil is at an angle of attack of 5 degrees, resulting in a 5-degree turn on the top side of the airfoil and a 15-degree turn on the bottom side of the airfoil. Using these numbers in the previous equations, we see that the downstream Mach number on the top side of the airfoil should be around 1.82, and the downstream Mach number on the bottom side of the airfoil should be near 1.45. Looking at the CFD simulation, we see that after the shock on the bottom side of the airfoil, our Mach number is roughly 1.435, while after the shock on the top of the airfoil, the Mach number is roughly 1.815. This simulation and its setup therefore show good convergence with theoretical values. The simulation used a free stream inlet condition where the Mach number was defined as 2 and a pressure outlet. It was run with an implicit steady solver, and the simplicity of the geometry allowed for a 2D simulation. You can clearly see the bow shock of the NACA airfoil, where the shock is curved, detached, and in front of the body, compared to the oblique shocks on the Diamond, where the oblique shock is straight and attached at the leading edge. The different types of shocks affect the drag in each. This is apparent as we see a difference of 6.265 kilonewtons of drag per unit span, clearly showing higher drag forces on the subsonic airfoil. It should be noted that the two airfoils were drawn to be of similar thickness and chord length. These simulations help show why we use high-speed airfoils at high Mach numbers, but further subsonic simulations could show how they do not perform well in such low Mach regions. Simply for the amusement, shock reflections are shown here. Thanks!